there's a lot of flexibility in the inflation picture. There's not arbitrary flexibility. You actually, those wiggles are a really important physics process. The fact that there are those wiggles there reflect a really concrete physics process that you're stuck with when you have an inflation theory, and other theories wouldn't have that process, and so it's a little bit better than what you say. I think what you describe is good enough, that you have theories with parameters and you can adjust them, but you can't adjust away those wiggles entirely. And so I think it's a little bit more than that. It's a pretty exciting thing. And so I think, so we've just been discussing some of the nice, that's pretty special. Like if we ask why do galaxies form in these patterns and not those patterns? Why are there these particular patterns in the microwave background radiation? We have an answer to that. We say it's the quantum vacuum state stretched onto the entire universe by inflation. And by the way, if you think about some of these competing ideas like cyclic universes and so on, they all share that feature, that they are finding one way or another to stretch the quantum vacuum across the entire observable universe. And so even though they're members of our community that love to debate which is better, to me the most deeply interesting part is the success of stretching the quantum vacuum out to cosmic scales and how well that works. So to me, that's really exciting. And we don't, maybe inflation did it, maybe something else did it, but that's a tremendous step forward, I think, to actually have something to say rather than just putting it in my hand. So we already know that we can do better than all the other physicists as we walk up and down the halls and they just say, well, choose the right initial conditions and get on with it. We can do better than that. We can have a story that these initial conditions came from the quantum field theory vacuum. And that's pretty special.